Now let's look at the limit comparison test for series. And it looks a lot like our limit comparison test for integrals. They've expanded on it a little bit. If we look here, as before, we want things to be positive. There's this idea of comparison going on underneath, and we'll look at that in just a second. But we need positive terms. Statement 1 says exactly what we had for integrals. If you look at that, we're taking the limit and we're seeing that the limit equals some constant bigger than 0. Remember, the interpretation of that is that you're showing that the two have the same growth rate, because out at infinity, the ANs are basically some constant multiple of the BNs, non-zero constant multiple. And therefore, whatever one series does, the other series does. So that is essentially what we had for integrals. And the proof of that is basically the same. It's a little tricky. We had to use an epsilon, if you remember, because we couldn't quite bound one with the other, but we could bound with some slight shift of the other. So we will dispense with that because you've seen that proof for integrals. But there are two new pieces they've added. So this first one says, well, what if the limit goes to 0? Now before we just said, try something else. But you can say something if the limit is 0, so long as the thing that you're comparing with, and notice that you really have to put the one that you're comparing with, the one that you know about, on the bottom. Because now if you know that that series converges, then your unknown one will converge as well. And on the flip side, if that limit's infinity, which before we said try something else, inconclusive, we can actually say something. If the thing you compared with, if that series diverges, and again, the key is it's on the bottom there, then you can conclude that your unknown series diverges as well. So let's see the argument for 2 and 3. It's really straightforward. For 2, we know that the limit as n goes to infinity of our a sub n's over our b sub n's equals 0, then eventually, so there's going to become a point. And remember, this is just a nice short way we say eventually, right? We're saying that there is some point big N, which after that, so for all terms after that, that ratio must be less than 1. Let's think about that. What does it mean for a limit to be 0? It means that that ratio is getting closer and closer and closer and closer to 0. Infinitesimally close, right? And so it's clearly got to be less than 1 if it's getting closer and closer to 0. Well, just multiply both sides by bn. And what do we have? We have that eventually all of our ANs are less than our BNs. And as part of our supposition, the ANs and BNs were positive, so I can say that. And we were saying that we were going to presume that the BNs converge. So really this boils down to a direct comparison test. The fact that that limit goes to 0 means eventually we can say this. We're less than a convergent, so the series of my ANs converges by DCT. And if you recall, the number 1, which I'm skipping, but we proved for integrals, also boiled down to DCT. So really all 3 of these, in their essence, are true because of some direct comparison. So we sort of inherit limit comparison from what we had in direct. So, so there's the 2 there. Let's look at 3. Well, kind of a similar argument, just reversed. Since that limit is infinity, then for big enough n, that ratio has to be bigger than 1. All right? that ratio is getting larger and larger without bound. It is definitely bigger than 1 at some point, which means that eventually, if you multiply the bn to the other side, all of our an's are bigger than our bn's. And again, we're assuming that we're talking about positive terms. And so if the bn's diverge, then the sum of the an's diverge by dct. Because again, that limit is telling us that eventually we have exactly what we need for a direct comparison test. The an's are all bigger, and this series diverges. So both of those arguments boil down to a direct comparison test. And number 1, which we're skipping, essentially says that you can do either one of these. That's why they'll both converge or both diverge. Whatever one's doing, the other is going to do as well. So these two parts are new. We didn't have these when we talked about integrals, mainly because we wanted to kind of introduce this slowly, this idea of comparison tests. We could have added these for integrals, but we didn't. But now you can. So not only can you make the conclusion if they are the same growth rate, but under the right conditions, you can make conclusions here. But it's not always, right? If this is infinity and the thing you compared with converges, you got nothing. If this limit's 0 and the thing you compared with diverged, you got nothing. So it has to be those two things together. The limit being 0 and the thing you compared with converges, or the limit's infinity and the thing you compared with diverges. And now that we have this added bit, it's important that you set that ratio up the right way, right? The bn's, the things you do know, need to be on the bottom. Really, in part 1, it doesn't matter, because if you flip that, you still get a limit that's bigger than 0, and we're only saying that they both do the same thing. But really, for these, the one that you don't know needs to be on the bottom, so I would just be in the habit of always, or excuse me, the one you do know, the bn's, needs to be on the bottom. I would just be in the habit of putting those on the bottom. So yeah, a little bit expanded, but it's the same idea that we had for integrals. So next I'll look at an example of using the limit comparison test.